Uh, so, hello everybody. My name is Misha Mazin, or Mikhail Mazin, Misha Mazin, okay. I'm also a colleague of David and Natasha from Kansas State. No, and well, I've been involved with math circles also for a lot of years. I went to some math circles when I was in school, and then I started teaching them when I was an undergraduate student back in Moscow, Russia, where I grew up. And well, I continue doing this now. So and I coordinate the math circle, the Manhattan Math Circle in at K State, and sometimes join Navajo Math Circles at summer camps or visits, school visits, and such. So that's a little bit about me. Now, so I'm a combinatorialist. So, like as a mathematician, a lot of my most of my research, well, big part of my research is in combinatorics, and well, combinatorics is basically about counting number of ways of doing something. So, I mean, that's kind of a very vague definition, but you will see what I mean in a minute. And That's also one of my favorite topics to do in with this uh, at math circles with the kids. So, and that's what I'll try to show you today. So let me share uh, uh, the my iPad screen. Start broadcasting. Let's see. Hopefully everything works. Yes, so here is my screen, and I'll go to Notability. Okay, so this is the problem list. So, by the way, some of the problems were inspired by this art of problem solving. So that's a really good resource. Might be towards the end, I'll talk a little bit about it and show you how it works. So, how it works, but they have a lot of very good material there. Anyways, so well, let's start. Let's do some math. Let's do some combinatorics. So basically, as once again, we are going to be counting ways to do various things. So here, and well, let's start with the first problem here. So here we go. We have three squares. So they're uh, here. Yeah, so these three squares. And we have five colors: green, blue, yellow, red, and brown. And we need to color each square in one color. And the question is, in how many ways can we do that? So, well, maybe, so if you have an answer, please put it in the chat, or we'll discuss it. And I want to see how. Uh, uh, right, 60. Okay. Any other guesses? All right. So there is a good right guess now. Okay. Okay. Very good. So let's see how it goes. So basically, what I want to say here is, so I like to say that there are these four principles in counting in this basic combinatorics, and they correspond to the four arithmetic operations. And so the first principle is the kind of the most maybe uh, probably the most important, I guess, is multiplication. So basically, the idea here. So this is maybe I should add a page here, and so this is multiplication principle. Um, So basically, the idea is that if we want to do something, want to do to count in how many ways we can do something, maybe we should split it into several steps. So here it is very natural, right? So we need to color three boxes. So it's very natural to split it into three steps. So first we color the first box, then we color the second box, and then we color the third box. So, well, and schematically, I like to draw this kind of tree here. So here, so we have this three boxes, and first, second, and third. And on the first step, I'll color the first box. And well, in how many ways can we color the first box? Well, we had what? We had five different colors, right? So there are five ways, right? So there is we can color it in green, we can color it in blue, we can color it in yellow, we can color it in red, and we can color it in brown, right? So there are five ways to do that. Five ways. Okay, so that was the first step. Then on the second step, we color the second box. Right, so maybe I put it like this. And okay, so in how many ways can we color the second box? Well, again, in five different ways, right? So we can color it in green, we can color it in blue, we can color it in yellow, and we can color it in red or in brown. Wait a second. Let me make it a little bit smaller so that things fit here. Uh, Brown. Okay, so and we can do that for in every case. So basically, it doesn't matter what was the color uh, of the first box. We have five different ways each time, right? So after that, after the second step, how many different ways in total did we get? Well, we have 5 times 5, right? So because for every 5 ways on the first step, we have 5 ways on the second step. So we multiply 5 times 5. So we have to multiply times 5. Right? And then on the third step, so what happens? So now, well, it will be really hard for me to draw because too many ways, right? But essentially, what happens is that for each way, we'll have five different options for the third box, right? And the same thing for uh, uh, for everyone there, and so on. So once again, oops, I'll need to multiply by 5. So in total, I get 5 times 5 times 5 options, which is 125. So that's the answer. So what was important here is that number of options on each step didn't depend on previous choices. So it doesn't matter what color we chose for the first box. There will be 5 options for the second box. So important thing uh, uh, is that number of choices on each step doesn't depend on previous choices. And because of that, we just need to multiply them, right? So we multiply number of choices on the first step times the second step and so on. So that's how our multiplication principle works. All right. So any questions on this one? Okay, so if not, let's go to the second problem. So that's a little variation on the first one, right? So what do we have here? We have, suppose that now no two squares can be the same color, right? So basically, if you look here, so here you can see that sometimes I would color the same box, oh, the different boxes in the same color. So for example, uh, so if I go like this, then both the first and the second boxes are colored in yellow, right? And so this is now forbidden. We cannot color them in the same color. Um, so, however, it turns out that this can be done in a very similar way. So let's try to do it step by step now. So, okay, step by step again. So we first color the first box. So how many different options do we have for the first box? How many options do we have for the first box? So far there are no restrictions, right? So we have right, we have five options. Five options for the first box. Right? But now the first box is colored, right? And now we try to color the second box. Second box. Oops, what is going on? Okay. Second box. So how many options now do we have for the second box? Four. Right. So one of the colors is forbidden. We cannot use the same color. So one color is already used and we cannot use the same color twice. So we have only four options. But you see, again, even though those options depend on the first choice, right? So if we use blue, then we cannot use blue. If we use green, we cannot use green. But the number of choices on the second step does not depend on the previous choice. So because of that, we can just multiply. That's really nice. Okay, and on the third step, how many choices do we have? So now we already colored two of the boxes. So two of the colors are already used and we cannot use the same color twice. So we have three options. And we just need to multiply all of them, right? So what do we get? We get 20 times 3, 60. All right. So here on yeah, so on the first in the first problem we had just five options for each of them, and we multiply them, and we get 125. And in the second problem, because of the restrictions, we get much less. So we get just 5 times 4 times 3, 60. Okay, so let's look at the third one now. So the same problem, but now the restriction is that uh, so the two boxes that are next to each other cannot be the same color. So if they're not next to each other, they can be, we can use the same color. That's not a problem. But if they're next to each other, they should be different. So you can think of it as a kind of, you don't want them to glue to kind of, you want to see where one box ends and the next one starts, right? So that's why you don't want to have two boxes next to each other in the same color. So what's gonna happen there? In this case. So, okay, so we do the same thing as before. We color them one by one. And I will start, uh, right, I will start from the left again. All right, so from just from the first box. So how many choices do I have for the first box here? So again, we just have five choices, right? So it's not very different. Right, because there were no restrictions. And then for the second box, well, I cannot do the same color, right? So it's going to be four, right? So four choices. Okay, so far it's kind of similar to the previous one. But now comes the difference. So how many choices do I have for the last box? So it cannot be the same color as the second box. It cannot be the same color as the second box, right? But it can be the same color as the first box. So basically, there is only one restriction, right? So only one color is forbidden. Uh, right? So that's the difference with the previous. So because in the previous problem, this third box, it couldn't we couldn't use two of the colors, right? We couldn't use the color from the first box and from the second box. But now we cannot use only one color, the color of the second box. So there are four options here, all right? And therefore we multiply and we get 80. Okay. So you see, you get kind of very similar problems, but with some variations and different answers. And you can explain where this different answer come from, because the restrictions are different. But the general idea is that you split the process into steps, and on each step you have the same. On each step you have the same number of um, choices, so it doesn't depend on the previous steps. And because of that, the answer is given just by multiplication, multiplying these numbers of choices. So that's multiplication principle. All right. So, okay, so let's go on to the next one, next problems. So, uh, and yeah, I like to start with this. So so yes. Well, maybe. Uh, uh, Spoiler alert. That is going to be addition principle or some. Yeah. So these problems are going to be addition. Uh, okay. So here is the first problem. Well, problem number two here. So we have four towns. We have A, B, C, and D. Those are towns, and they're connected by some roads, like in the picture. So there are two roads from A to B. There are two roads from A to C, three roads from B to D, and one road from C to D. Uh, and the question is, in how many ways can we get from A to D without kind of going backwards? So I don't want to return if I already been to A, if I left A, I don't want to go back to A, right? But I need to get to D. How many ways can we do that? Right, so I already get some correct answers, but I do want to see the computation. So let's first ask how many ways are there through B? Through the town B. If you go through the town B, then how many ways are there? Right, so we have everything. Okay, okay. So if we want to go through B, then we actually use the multiplication principle, because on the first step we have two choices, and on the second step we have three choices. So there are six ways to go through B, and then if we want to go through uh, C, then, well, on the first step, we have two choices, and on the second step, we just have one choice. So that's two. And here comes the addition. Now we need to add them. Right? So 6 plus 2 is 8. So essentially, what the addition principle tells us is that sometimes we have kind of completely separate options, completely separate ways to do certain thing, and then we just need to count them separately and add. So that's very kind of straightforward idea. But it's kind of a casework. So you say that, okay, so there is this case, and we count it separately. Then there is this case, and we add them up. But this first problem was, of course, it was very visual, that you have two different ways, different kind of parts that you need to count separately and then add up. But let's have a look at the next problem here. So a number is called lucky. Uh, Lucky if the sum of its digits is even. So for example, I don't know, let's see. So if I take 5, 7, 2, 3, well, that's unlucky, right? Because we have 5 plus, okay, what am I doing? 5 of 5 plus 7 plus 2 plus 3 plus 3. That is 17. So that is odd, right? So that is unlucky.
Misha,
Yeah.
Kim is asking if leading zeros are allowed.
Ah, right. So no, no. Yes. So three-digit numbers cannot start from zero. Yes. Very good question. And that's a very yes. I mean, of course, it's a matter of convention, but yes, usually if you say three-digit number, that means that it cannot start with zero. So if it starts with zero, then it's probably a two-digit or one-digit even. Yeah, very good question. And that kind of changes the count then. Okay, so that was unlucky, but maybe if I take something else, say, I don't know, 5 to 3, that is lucky, right? That is a lucky number. Okay. So now the question is how many lucky numbers, how many three-digit lucky numbers are there? So, uh, well, I don't know. So, and remember that we are doing this addition principle. So there are probably different options, different kind of types of lucky numbers, and I would suggest counting them separately. So, what do you think? What are the different types of lucky numbers that we should count separately here? So, any ideas? So all digits even. So that should be one type. So we'll count it separately, right? Uh, yes. Another option is one digit even and two odds. And one even, two odd. But I would suggest actually splitting this one into, well, maybe into three parts. Further splitting them into three parts. What these three parts would be? I should have more space. Uh, but yeah, suggest. Yeah, another page. Okay. Okay. So what do you think? What are three parts here? How would you split this uh, when there is one even and two odds? What are the natural way to split it into three parts? Well, okay, so let me say this. I'll just tell specifically which of the three digits is even, right? So I can have the odd on the first place. Okay, doesn't fit. Okay, let me abbreviate. Odd, even, even, right? And then I can have even, odd, uh, even. Oh, sorry. I have to. Yes, I'm messing this up. So there should be one even two odds, right? Yes. So, okay, I can have the even on the first place, even, odd, odd. I can have uh, it on the second place, and I can have it on the last place. Okay. Okay, odd, even. Okay, so these are going to be the four different uh, options, and we'll count them separately. By the way, maybe Okay, let's just have a look. Okay, so let's first do all digits even. So how many different three-digit numbers which have uh even okay. So yeah, so we have digits, right? So how what so digits uh we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so the digits that are divisible by 2 are even, right? So the uh, even digits are 0, 2, 4, 6, and 8. Those are even because they're divisible by 2. 0 is divisible by 2, so it is, if I divide 0 by 2, I get 0, right? So it is even. And I have odd, the rest are odd, right? Five even, five odd digits. So now, okay, we have a three-digit number. We have three-digit numbers, three-digit numbers, uh, uh, like this, and all digits are even. How many numbers like that do we have? So this is kind of similar to what we did in the first problem, because we have three positions and we just need to choose. We can just fill these positions one by one. So how many options, how many different digits can be on the first position? Four, exactly. So we have five even numbers, five even digits. However, zero cannot be there. So we have four options there. How many options do we have for the second position? Five, right? So because we for the second position, zero, we can use zero, so we can use any even digit. And then for the last position, we also have five options. And note that it doesn't matter what we put in the first position, the number of choices is always five for the second and then five for the third. So that's what we get here. So this is what? This is 100. Okay. Now, well, let's look at the next option. So we have even, odd, odd, right? So how many options do we get here? So how many options for the first digit? So that is again going to be 4, right? Because even we cannot use 0. So it's going to be 4. Then for the second position, we'll have 5. And for the third position, we'll get 5, right? So that's kind of the same 100, kind of similar to the previous. However, here we are going to have a different answer. So why is that? So how many options do we have for the first digit here in the third option? Right, so we have an odd number, odd digit. And for odd digits, we can use any of the odd digits, right? So because 0 is not odd, so we can use 1, 3, 5, 7, or 9 there. So no restriction there. So we have 5 options. And then for the other two, we'll have 5 options as well for both of them, right? Because there are no restrictions. There are 5 even digits and 5 odd digits, and we can use any of those. So we got, what is it? 5 times 5 times 5. This is 125. And the third question is, it's 5 times 5 times 5, right? Because we start with the odd. So kind of the reason why I insisted on splitting this into three different options is because it kind of this case when we start with the even is special because we have more restrictions and less options then. But here we get again 125. And now we just need to add them up. So we got 100 plus 100 plus 125 plus 125. So that is what? 450. All right. Okay. So any questions here? All right. Um, okay, if there are no questions, let's look at the next one, next problem. Um, So it's kind of similar, but now instead of lucky numbers, we have cozy numbers. So a number is called cozy if every digit is either 3 or it is next to 3. So one of its neighbors is a 3. So for example, so here we have this number. So that is cozy, right? Because we have 6 is next to 3 and 2 is next to 3. And so that is a cozy number. And this 3783 is also cozy because 7 is next to 3 and 8 is next to 3. So that's cozy numbers. But this one is not cozy. 2, maybe let me use a different color. So this one is not cozy because 2 is not next to 3, right? So that's not a cozy number. Okay, so now the question is, yeah, we want to count cozy numbers. How many cozy numbers do we have? So we start with counting the two-digit cozy numbers. Uh, so for the two-digit cozy numbers, and again, so we want to do some kind of casework. So we need to look at different options. So what are going to be options that we're going to count that we probably should count kind of separately. Um, so two digit, right? And they should be cozy. So what are the different options we should look at? Right. So we might have three and something, or we can have something and three. I would also consider separately 3, 3. And then I will insist that in the first two cases, that other number is not 3. Okay? So that we kind of don't double count. All right? Uh, okay, very good. So how many options do we have here in the first case? In the first case, how many options? 10, right? So the second digit can be anything. Oh no, 9. I'm sorry, 9. So I don't want to count 3, 3. So I don't want it to be 3. So not 3. And here I also don't want it to be 3. Not 3. All right, because otherwise I would double count. So I kind of want it to be I want to kind of yeah to indicate all the threes kind of already. Okay, so there are 9 options here. So how many options in the second case? So this digit, it cannot be 3, but it cannot be 0, right? So it cannot start from 0. So there are 8 options there. And, well, this one is just one number. So it's 1. So we got 9 plus 8 plus 1. So that is 18. There are 18 different, 18 cozy two-digit numbers. All right. Okay, so let's try now the three-digit cozy numbers. So what will happen with three-digit cozy numbers? So what are the different types of three-digit cozy numbers we should count separately? So, okay. So the first one. Well, okay, yeah, 3 in the middle. Great. Okay, let's put 3 in the middle. Actually, let's count right away how many of these do we have. And but I want to insist that these two numbers are not threes. Oops. No, these two other digits are not threes because I want to avoid double counting. Um, uh, Double counting. So here it should be uh, this. Aha. Okay. Another case is when they're all threes. That's good. Uh, okay. Uh, okay. So what are other cases? What more do we have more cases? Well, otherwise we would have to have uh, so we can have uh, something like this, right? That's also cozy. And then I have to, since I insisted that these dots are not threes, I would have to consider 3, 3 dot and then uh, dot 3, 3 separately as well. But I think that's it, right? That's all the possible configurations of threes. So let's now count them all separately. So how many? I think the first one is actually the most complicated one. So how many options do we have here? So how many? Right. So we have how many options do we have for the first digit here? It's 8, right? So because it is not 3 and not 0. And how many options do we have for the last digit here? That is going to be 9, right? Because 0 is allowed there. So we got 8 times 9, which is 72. All right, so this one is easy. How many options do we have here? There is just one option, right? So this already there are no choices there. All right, so now here, how many options do we have? So this uh, dot is in the middle, so it can be anything. So except for 3, right? Because we don't want it to be 3. So this is 9. This one is also 9 because it's in the end. It can be anything except for 3. And this one is then 8 because it cannot be 3. All right. So now we just need to add it all up. So we got 72 plus 1 plus 9 plus 9 plus 8. So how much is that? 1899, I think. Right? Is it? Yeah, I think that's correct. All right. So that is addition principle. So sometimes when we count options, we need to split our configurations into different parts and count every part separately. So that's addition principle. Oops. Right. All right. But I promised you more, right? So we should have also deletion and subtraction. Well, before we get there, I have a few more kind of problems uh, that I want to discuss. Uh, so, next problem. Uh, so here I have 5 different books, and I would want to arrange them on the shelf, right? So the question is, in how many ways can I do that? I can put them in any orders, in any order. So basically, the question is, how many different orders do I get? So let's see. Let me add a page there. Where? No, here. Add a page, maybe. And let's say I have 5 books. And just for simplicity, for me, oops, they're going to be of different colors so that we can keep track. Uh, so 5 books. And we want to arrange them. Right. 5 times 5 times 5 times 5 times 5. That's actually too much. So the idea, of course, is to do kind of a multiplication principle. So we'll put the books on the shelf one by one. So so we put books on the shelf uh, one by one, one book at a time, at a time. But I just have 5 books. So, okay, so on the first step, first book, so how many choices? For the first book, we'll have how many choices? Ah, right, yeah, so that is the correct answer there. Of course, so for the first book, we have 5 choices. But then for the second book, we already put one book there, so on the shelf, right? So there are only 4 books left. Second book, 4 choices. Then the third book, we just have 3 choices. Then there are only 2 books left, so we have 2 choices. And then the last book, well, there is no choice. It's just one book left. So it is 5 times 4 times 3 times 2 times 1, which is indeed 120. And this number uh, 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 it kind of it so this kind of situation when we have this count without repetitions essentially uh, it happens very often and because of that mathematicians even have a special notation for it. So it is 5 factorial and we just write 5 and exclamation sign there, so this is 5 factorial. So that's just a special notation. So for example, okay, so basically 1 factorial is just 1, 2 factorial is 2 times 1, so that is 2, 3 factorial then is what? 3 times 2 times 1, so that is 6, 4 factorial is going to be 4, and in fact, it's okay, 4 times 3 times 2 times 1. So for computational reasons, you can notice that it is just 4 times 3 factorial, right? So this is 4 times 6. We already computed 3 factorial, so it was 6. So this is going to be 24. And then 5 factorial is going to be 5 times 4 factorial, right? So this is 120. And you can continue. Okay, 6 factorial is going to be 720, so on. So it kind of grows fast. So after that, it's really becomes large number. Okay, so that's another multiplication type of problem, but I wanted to use it, and it's to introduce this important notion of a factorial. And that's kind of one of the standard problems that allows us to introduce these factorials. Mm. Uh, and the next 2 problems are kind of variations on this idea. So maybe actually, let me skip number 6 here. Let's just skip it. I will leave it for you to think about next time on your own. Let's go to the number 7. Because, okay, spoiler alert, this one will use another principle that I call subtraction principle. That is why I want to talk about it now. All right. So here is the problem. In how many ways? So I have three different math books, and I have 4 different history books, and I want to arrange them on the bookshelf just as before. Uh, but I have this a bit of a strange condition. I want at least 2 of the history books to be next to each other. So, uh, So that is a little bit of a strange condition. And if you start trying to do it as we did before, it will be a little bit challenging because you don't know at what point you put the two history books together. And depending on that, you'll have different number of choices on the next step, right? So all this idea that on each step you have the same number of choices will kind of fall apart, and it will be hard to, and we don't know how to count it. So that's why we have a hint here. The suggestion is to first count kind of the opposite thing. So let's find out first in how many ways can we arrange uh, these textbooks so that no history books are next to each other, so that they alternate, um, so that they always alternate. So basically, so since we have three math books and four history books, what that means for us is that so for the hint, so if we have this no two history books, let me put H history books are next to each other. So since we just have three math books and four history books, that would mean that they have to go like this. History book, then math book, then history book, then math book, then history book, then math book, then history book. That's the only pattern possible there, right? So in any other pattern, we would have two history books next to each other. That's the only way to separate them. Uh, so now all we need to do is to find, but yeah, remember, the history books are all different, right? So it's not like just one way to put them in such a pattern because history books are all different and math books are all different. So there are more than one pattern here. However, we can now, since we know the pattern, we can count number of options. So we know the pattern, and now let's now just put the actual books on the shelf one by one, left to right. So how many options do we have for the first history book, the one on the left? So how many options there? Right? So it can be any of the history books. So how many history books do we have? So in the problem we had what? Four history books. So there are four options there, right? For the history book, for the first history book. Now, the next one is the math book, right? So how many options for the first math book do we have? Three, because it could be any of the three math books. Then we have the second history book. So how many options do we have for the second history book? Three, right? Because we already put one there, so there's one less. And then for the second math book, we'll have, well, two options, right? Because there are two math books left. And then there are two options for the next history book. And here actually there are no options, but well, just to complete the pattern, that's put one and one there. Right, so that's how many options are to put the books in this pattern. And that's the only pattern that allows us to separate all history books. So by the way, it might be, if we could have done it in slightly different order, we could have first put all the history books, right? And that would be 4 factorial, right? And then we could have done all the math books. That would be 3 factorial. So we got actually 4 factorial times 3 factorial. So this is 24 times 6. Okay. So this is 120 plus 24. Or it's 20. It's actually 12 squared. So this is 144. Right? Yes. So 144. Okay, but that was not the question, right? That was number of ways to arrange them so that all the history books are separated. Uh, so the idea here is now to count all possible ways to put those all those books on the shelf, and then just subtract these, right? Because that's the subtraction principle. So we counted the complement, we counted the bed arrangements, and now we just count all arrangements and subtract. So what is the total number? Total number of ways to put all seven books on the shelf, right? So that's kind of similar to the previous problem, actually. So now we just have seven books. We need to put them on the shelf, right? So it's like here. Well, I don't have to actually count it. I'll just write 7 factorial. So it's 7 times 6 times 5 times 4 times 3 times 2 times 1. So sometimes I get lazy and I just leave it as 7 factorial. But if you want to compute it, well, this is going to be 7 times 6 factorial. And I already computed 6 factorial, right? It was 720. So it's 7 times 720. Okay, that's a lot. So 7 times 7 is 49. So, okay, I'll write it that way. 4900 plus 7 times 20, which is 140. So this is actually 5040. So that is 7 factorial. Yes. All right, so that was the total number. So now what we need to do is to subtract. So we have 540 in total, and we need to subtract 144. So what we got? We got 4,896. That's the final answer. So basically, the idea of the subtraction principle is that sometimes it's easier to compute the complement, the kind of the bet. So if you have some kind of condition on the arrangements that we want to count, sometimes it's easier to count number of bad arrangements, arrangements that are forbidden, and then you just take the total number and subtract the bad ones. So here the reason was that the bad arrangements, the pattern was there was just one pattern possible for the bad arrangements, but for the good arrangements there is a lot of patterns. So that would be kind of a lot of cases that we would need to compute separately, and that would take a lot of time. So yeah, so that's why it was convenient to use this subtraction idea for this problem. All right. So any questions here? All right. And let me, I just uh, trying to see how much time do I have so that yes, I have about 20 minutes, I think. Um, just trying to gauge what we should do next. All right. So actually, so far, as you might have noticed, we had multiplication, we had addition, and uh, we had subtraction, right? So there is one more principle, the deletion. So we should some principle. So we should encounter some situation when we need to divide. So let's try to uh, find out when we need to divide. So here is the next problem. We have four kids, Anne, Bob, Marie, and Tom. So they are a team, all right? And they need to choose a captain, and a deputy captain. So two people. Uh, uh, right. Uh, okay, so we need to choose a captain and a deputy captain. And the question is, in how many ways can we do that? So Okay. So any ideas? What would be the answer? So how many ways, in how many ways can we do that? So there are four kids. They need to choose a captain and a deputy captain. So how many choices do we have for the captain? So let's first choose the captain. Four choices, right? So any of the kids can be a captain. So basically, uh, we can have uh, we can have Anne to be a captain. We can have Okay, so maybe I shouldn't. Yeah. Okay, but after we chose a captain in four different, we chose a captain. How many choices do we have for the deputy captain? Three, exactly. So, right, so because one of the kids is a captain and that should be somebody else. So we have four times three, 12. So it's again just the multiplication principle. So in fact, I want to, just for the purpose of the next two problems, I want to actually list all of these options. So we have 12 options, right? So we have, okay, so maybe, yeah, let me write it that way. So we have captain, and then we have deputy captain. So we can have Anne uh, and Bob, for example. We can have Anne and Marie. We can have Anne and Tom. Then we can have Bob and Anne, Bob and Tom, and Bob and Marie, right? Uh, we can have Tom and Anne, Tom and Bob, Tom and Marie. I switched them. Okay, anyways, that doesn't matter that much. And then we can have Marie as captain and as deputy, Marie and Bob, and Marie and Tom. So that's all the 12 options. So we can see. So for each captain, we have three options for the deputy. Okay, so I listed all of them. Now, let's look at the next problem. So now, instead of choosing captain and deputy captain, what they need to do is to choose two representatives. So basically, they need to choose two of them to play in a tournament of 2v2 uh, volleyball game. So, all right. So Uh, at first, you might think, well, it's the same thing. We need to choose two people, and in the previous situation, we also chose two people. However, the answer is going to be actually different. So let's have a look at these choices. So here we have uh, these 12 options, right? But now let's try to use these 12 options to form this team, right? So we have one, two, three, four, five, six, 7, 8, uh, 9, uh, 10, 11, and 12 options. And now we just look, okay, let's just use these options to form teams. Are there going to be 12 different teams here? So say, for example, for the first option, we can just take Anne and Bob and form a team, right? So how many different teams do we get here actually? Six, right? Because actually the first option and the fourth option, they are the same, right? And okay, so this second option is the same as which one? So let's find the other one. Which option is the same as the second? Number 10, right? So number 10. So you can see that all of them, they're kind of common pairs. Oops, what did I do? Okay. Uh, yeah, they're all common pairs. So number 3 is the same as number 7. And number what? 5 is the same as number 8. And then number 6 is the same as number 11. Finally, number what? 9 is the same as number 12. So they all come in pairs. So because of that, we kind of what we need to do. So we kind of what we can say that we need to choose the first person uh, first. Then there are four choices for the first person. Then we have three choices for the second. But then we need to divide by two because we double counted. We counted divide by two because we counted every team twice. So the answer is then six. So basically, the idea here is like this. So if we want to split the process in two steps and choose the first player and then the second player. However, if we do so, then we overcount because we count every team twice. If we choose the same two players in the opposite order, it's going to be the same team, right? So because of that, the answer is different. It is six, and that's why we need to divide. And that's kind of the division principle. Sometimes, if you do things step by step, you get some symmetry, and you need to divide. That's the idea. So let's look at the next problem. Uh, so surprisingly, I mean, it's again a very similar formulation, similar situation, but surprisingly, it's going to be again a different answer. So let's see what happens. So in the end of the day, the same kids decided to play a game of volleyball, 2v2 volleyball, just between themselves, right? So now what they need to split into teams and to play against each other. So how many different ways are there to split uh, uh, into uh, to split into teams? Right. So right. So let me. Yeah. Right. So it's first. You might think, okay, maybe it's the same thing. We just need to pick the team, right? Pick the first team. Pick the first team, and there are six different ways to pick the first team, and then the remaining two kids will form the second team. However, here we are again overcounted by two. Why is that? Because let's say that we chose that we choose Anne and Bob for the first team, right? So that's our choice for the first team. Then the second team is going to be Marie and Tom, right? But if we choose Marie and Tom for the first team, it's going to be the same thing again. So these two are again the same ways to split into two teams, right? And then this one, so this is Anne and Marie in the first team. Then in the second team, it's going to be what? It's going to be, uh, okay, let me put kind of, it's going to be Bob and Marie. No, I was wrong. Right. Yes, it should correspond to what? So Marie, Anne and Marie are in the first team, then Tom and Bob should be in the second. So that's the blue one, right? So the blue thing. That's another kind of way to split it. And then finally the blue and the yellow are the same way to split. So basically what I'm saying is that we have six different ways to pick a team, six ways to pick a team. But then we need to divide it by two again because the opposite team, it's kind of, yeah. So still need to divide by two uh, because of the overcounting, because of the symmetry. All right, so the answer is three, right? So that's kind of interesting here. So we have three very similar problems, but answers are different. And the idea how we kind of approach it, how we count, is that we count the first problem, and that's just multiplication principle. And then we just see that while we were doing that, we overcounted by a multiple of two for the second problem, and we overcounted by a multiple actually of four for the third problem. And we have this division built in because of that. So that's kind of division principle. Okay. Yeah, so very good. So somebody uh, listed the ways to split, and there are only three of them, right? So there are six different teams possible, but the ways to split, it's just three because each way to split, it takes two teams, actually. All right, very good. So, all right. Yeah, I think this will be a kind of our last problem here. Maybe I should actually. Maybe I'll yeah so this and so this is a very kind of important type of problem in combinatorics. Here we just need to choose several items from a group of items. So for example, in this problem we have five different pieces of candy and we need to choose two of them. And the question is how many ways can we do that? So the idea here is very similar to what we just did before. Uh, so in how many ways can we pick the first candy? There are five pieces, so there are just five different ways for the first candy. And then how many ways are there for the second candy? Yeah, first candy, we already picked the first candy, so there are only four options left, right? So there were just physically five candies, five pieces of candy, right? And so we pick one, and now we need to pick the second, right? So there are only four options for the second. Okay, so do you think this is the correct answer? So there are other 20 different ways to pick two pieces of candy. What do you think might go wrong here? So maybe there are five pieces of candy. I'm not very, so maybe I'll just draw little circles for this candy. I cannot really draw, don't want to draw. So that's five candy, five pieces of candy. They're all different. Now maybe I pick what? Red and blue, right? So that's one way. But note that if I first picked blue and then red, well, that's the same thing, all right? So I don't really care in which order I pick them. So the question is, how many different in how many different ways Anton can choose two candy, right? So it's not like he's picking one and then picking second, and we don't need to keep track of which one was first and which one was second. So if we multiply 5 times 4, we count in how many ways we picked the first and then the second. But you see, if I first picked red and then blue, it's the same two candies as if I picked first picked blue and then red. So similar to the previous problem, what we need to do now is to divide by 2. Yeah, so that's going to be 10. There are only 10 different ways to how we can pick two candies uh, out of out of 5. Because yeah, once again, red and blue and red is the same thing. So every way is if we multiply 5 times 4, we counted every way 2 times. So we need to divide by 2. All right. I think I should probably not go further. I think everybody's tired. So what I want to do in the remaining few couple minutes is to maybe show you some an interesting a resource that I used actually for this for some of these problems. And there are more problems down there. So you can look at the PDF. So basically, so this you can see in the beginning that I wrote that this is inspired by art A of PS. A of PS is art of problem solving. Solving. So that's a web page solving, and they have a lot of resources. So they have courses like online courses. They're kind of pricey, but there is a part of this website that is free, and I want to show you how it works. And I think they have really good problems, really good materials there. Okay, so let me stop sharing this thing for a second. Not first, just stop sharing. Let me share on this one instead. Where am I? I'm sorry. Yeah, I want to. Yes, here it is. Okay, so this is the web page. So this is artofproblemsolving.com. So if you just go to maybe to the beginning, so that's so you need to create an account to be able to use it, but it's very easy. So just email. You just need the name email. So if you go into so there is an online school and there are some classes, but they are a little bit expensive. They are very good though. Anyways, but the free part here is this Alchemist. And well, let's play. So basically, this is a huge. There is a huge number of problems here on various different topics, and it's kind of interactive. Not interactive. Well, it's adaptive, so it gives you a harder problem next time and such. So if you press change focus, you can see that there is a lot of different things. So here, the subject area, so it starts with pre-algebra, so you can go into arithmetics, just addition, and here it is. You just need to compute some sum, right? Very good. You can do multiplication, negative, subtraction, all kinds of things here. And it goes all the way to pre-calculus. Well, actually, there are some very advanced things here. So if you look into intermediate algebra, for example, there are, I don't know, there is Cauchy-Schwarz inequality here, and there are problems for Cauchy-Schwarz inequality. Here you go. So kind of advanced stuff. So the part that that is most closest to what we talked about today is counting and probability. So counting basically is the combinatorics, and then you can use the counting to solve some problems with probabilities as well. We didn't get there, but that's just there. So for example, there are factorials, right? So you can set focus to factorials. And here you just need to compute something. Well, what is this? This is, well, actually, it's yeah. So how do you compute this? Actually, it's kind of easier to divide, right? If you divide 6 factorial by 5 factorial, you got 6. And if you divide 4 factorial by 5 factorial, you get 1 over 5, right? So it is 6 plus 1 over 5. It's probably not gonna accept the answer in that form. Well, let me press. It didn't like it, right? So, well, but yeah, so it's because, but if you put 6.2, it's probably gonna accept it. And then it explains the solution, and then it gives you a next problem to work on. And that's more interesting, right? Uh, okay. But I just wanted to show you this resource. There is a lot, so that's kind of something. Yeah. So let me stop here. I think that's all I wanted to say.